And the first weeks of the course, talking about what really is an inverse problem, what is it that characterizes an inverse problem, what are the inherent difficulties, how can we discretize these problems so we can handle them on a computer. And then we looked at a few regularization methods that actually try to deal with the way that errors are blown up if you solve the problem naively. And in particular, Ichu talked about truncated SVD and Tikhonov regularization, and it's all very good. Now, the thing is that we have set the stage for solving these problems, but we still need to talk about choosing that regularization parameter. So for truncated SVD, it's the parameter K that defines how many SVD components you actually want to include in the regularized solution. And for Tikhonov, it's a continuous parameter here, lambda, that sort of balances the weight you put on minimization of the residual and minimization of the norm of the solution. Right. Now, quite often, if you work in an interactive way on the computer, you can try different Ks or different lambdas. You can look at the solutions, and then you can somehow see, probably this solution here looks good. I'm very happy with that. And another choice is maybe to do a Picard plot these components, SVD components and the singular values, and there look at the noise. Where does the noise level start to influence the right-hand side? And by doing that, you can also sometimes eyeball what would be a good regularization parameter. So that's all very good. But we would like to automate the process. We would like to actually have methods around that can try to compute a good regularization parameter without any interaction from the user. And of course, sometimes you need to do this in a computer system that spits out regularized solutions. So that's what we're going to be looking at today. Find some mathematical principles for choosing these regularization parameters. So we're going to cover a lot of ground today, right? And to do that, before actually getting to these methods, we'll spend a bit of time looking into what is it really that is going on when we do regularization. And this insight will then give us some ideas to methods for choosing the regularization parameter. And after that, we'll talk about 4 different methods: discrepancy principle, generalized cross-validation, something called the L-curve, and the NCP criterion. So it's a lot of ground to cover today. So let's see. And I think a lot of the discussion today will take its basis in Tikhonov regularization. Just to summarize, and set the stage for these discussions, let's just remind ourselves what Tikhonov regularization is, right? So here is the Tikhonov regularization problem. You see, you minimize this combination of the 2 norm squared of the residual and the 2 norm squared of the solution. And by including this here, we avoid the norm of the solution blowing up due to the errors. And then we have the regularization parameter sitting there that balances these 2 guys. Right. Okay, so here's a bit of interesting notation. It's fairly easy to derive this particular relation here for the Tikhonov solution, right? So this is an equation that we use for doing analysis, for getting insight. This is, of course, not how you compute the Tikhonov solution. It's an equation that we use to analyze things, right? Yeah, for example, we don't like this matrix here. It squares the condition number of A, and a condition number is already pretty large, so squaring it is a really bad idea. Anyway, so you see here there's a matrix inverse here and a transpose of B, and And this guy here, the big guy here, everything in front of B, we give a name. Right, because we're too lazy to write this every time, so we just give it a name. And so I call it a regularized inverse. It's not really an inverse, but it resembles an inverse. I call it a regularized inverse because there's a regularization parameter sitting there. Okay, so whenever you see that symbol there, just remember that it is really just a shorthand for that guy there. And the key point is that you obtain the regularized solution by multiplying that matrix there to the right-hand side, to the data. Right. Okay. Okay, so we're going to be using that a lot. Also, I remind you of the noise model, which is like really, really simple. So the given right-hand side is an exact right-hand side plus some noise. And at least in this course and in our experiments, the noise is often Gaussian, although that's not really the case in practice, but it's easier to deal with when we're doing the exercises. And the exact solution, the exact right-hand side, the exact data, comes from applying the forward operator here to an exact solution. And of course, what we're trying to recover from the noisy B is a good approximation to the exact solution. That's what we're trying to do with regularization, with Tikhonov regularization, provided we can find a good lambda. Okay. So there's the notation again. So let's see. So if you start surveying the literature about regularization parameter choice methods, you will find many papers that do the following analysis. Okay, so they assume that we know what I call the noise level, the true norm of the noise. Then they look at a parameter choice methods, a particular method for choosing lambda. Okay, and then they study what happens to the regularized solution as the noise level goes to 0. Okay, so these are theoretical studies. They let the norm of the noise here go to 0. Then the parameter choice method should certainly satisfy that the regularization parameter should go to 0, because if there's no noise, we don't need to regularize. And also, this kind of analysis is then interested in showing that the regularized solution actually converges to the exact solution. So that's certainly a very important aspect of these methods. If there is no noise, then we'd like to make sure that we compute the exact solution. So that's fair enough. That's fair enough. For setting the stage for analyzing the methods. But the point of view I'm taking in this lecture here is a little bit different, because in a typical situation, you have a set of measurements, and there are some errors in there, and they are fixed. And our noise does not go to 0. It's not that if we sit long enough or wait long enough, our noise will go to 0. The noise is there, and there's nothing we can do about it. And we can't just go over and repeat the experiment and then hope that there will be no errors the next time. So that's certainly one thing that is the outset for this presentation here. And the other is that in some applications, we don't really know what the true norm of a norm is. Of course, if you're a mathematician and you define your problems, then you know it, because you just write it down and then you know it. But in practice, it's not always the case that you can go to the guy in the laboratory and ask, okay, so what's the true norm of the noise on your machine here? Tell me that. Sometimes they can give a guess, but not always. So I'm going to be talking about the situation where we may not know this, and definitely the errors are fixed, so we are not in this situation where the errors go to 0. Anyway, so that's fun. Let's see what we can do with that. You have already done experiments, of course, showing the influence of the regularization parameters. But once again, let me just show here that it really matters. So here's an image deblurring example. Here's the sharp image. And here's the blurred version. I know my point spread function here, so I know my matrix A. By the way, there are lots of very, very nice and interesting pictures on NASA's homepage, and you're free to use them. So this is taken from a NASA homepage. Some really nice and interesting, very detailed pictures. Right, okay. So I used Tikhonov regularization to try to reconstruct that guy here. And I tried different values of my lambda. So here, lambda is quite large. And I don't really get a very good solution. It's over-smoothed, right? There's too much regularization going on. I suppressed all the noise clearly, but I also have a reconstruction error, so that's not particularly good. Actually, this is worse than a blurred image. Okay, so I could try like a really small lambda. That means I don't do very much regularization, and I get the picture over here, and sure enough, now there are more details, but there are also some fake details, right? So what seems to be maybe very interesting details here on this planet is really just influence from the inverted noise, right? It's something that is not there in the exact image. So it's because some of the noise is now coming into the reconstruction. So somewhere in between the too large and the too small lambda is a good regularization parameter. It might be that one there, maybe. So anyway, how can we define methods to choose that one there automatically? Right. Let's see. So there are at least two different kinds of errors that we can look at, and we have to understand both of them and understand the difference here. Right. So again, on top here, we just have the problem formulation, the Tikhonov problem formulation. And you could argue that, all right, what you do is you when you define the Tikhonov regularization parameter here, you minimize this guy here, like a scalar function here, and which is a function of lambda, right? So maybe a look at this guy here would give you information about how to choose lambda. Well, it doesn't. It's not possible to choose lambda just by looking at this sum here, the weighted sum of these two norms, believe me. So unfortunately, it's more complicated than that. So let's look at instead at the forward error and the backward error. Okay. The forward error is the difference between the exact solution that we're trying to reconstruct and the regularized solution. All right? Okay, and here is where we plug in the expression here for the regularized inverse that we had on slide 2, and we plug that in, and we move things around a little bit, and so we end up with that expression in here. All right, and if you look at that, you'll see that we have like one component here that involves the exact solution, and another component here that involves the noise. Right. So the last component, the regularized inverse times the noise, is of course what happens to the noise as we do a reconstruction. And the noise, which is a part of the right-hand side, is actually influencing the solution in this way here. So it contributes to the error. And if there were no noise, then this noise error here, perturbation error, would not be there. The other component here, okay, that's what happens to the exact solution, because we do need to regularize to get rid of some of the noise. But that also means that the regularized inverse here is different from the ordinary inverse. Okay, so that means that the identity minus the product of the regularized inverse and A, that's not a zero anymore, and therefore something happens to the exact solution, and that's what we call the regularization error. Right. And really what we would like to do, one perspective of doing regularization is wouldn't it be nice to choose a lambda that sort of balances these two guys? If they are approximately of the same size, then that might be a good regularization parameter. So that's a good principle. We can't do it in practice, of course, because we don't know x exact. Okay. So anyway, the other error that we can look at is something we're going to call the backward error, or very often it's called the prediction error. Okay. So now we go to the right-hand side, and we look at the difference between the exact right-hand side. We don't know that in practice, but as we're doing theory here, we can still write it there. And then we look at the difference between the exact data and the predicted data, which is A times the regularized solution. And then you could say, okay, maybe we should choose a lambda such that we, with the Tikhonov solution, we predict the exact data as good as possible. Or we minimize this prediction error, or a backward error in the language of numerical analysis. And again, if we plug in our regularized inverse, we get an expression that is somewhat similar to the expression for the forward error. Again, we can see that we can break up the error into two components, one associated with the noise and one associated with something exact, here the exact data. And again, in principle, we would like to balance those two errors there. So in principle, that is what we're trying to do, isn't it? Okay. Let me say a bit more about the forward error. Let's see where I'm going. Yeah. All right. And in fact, here, the next thing I do here is that I throw in my singular value decomposition, and I throw in my filter factors for the Tikhonov solution. All right. So it will look like that. Let's see. You see the regularized solution there. We obtain that from the data. First we multiply with the U vector transpose, we divide with the singular values, we multiply with the filter factors, and then we multiply with V to get back into the right basis. And then again we can move things around. And so this is just a different expression for the regularization error and the perturbation error. But now it's expressed in terms of the singular value decomposition, and now we can see the role of the filter factors. Right. So you can see, for example, if all the filter factors are equal to 1, which means we don't regularize, we don't do any filtering, then of course this guy here is going to be an identity, and if the first term vanishes, but then of course we're going to have a lot of noise coming in here. On the other hand, if all the filter factors are small, meaning we do a lot of regularization, we do a lot of filtering, then we kill a lot of the noise. But unfortunately, then we have here that the I minus the filter factors is essentially just an identity, and we get a lot of this error component there will be large. Right. And some more terminology that you'll see in the literature about the regularization error again here. Well, here it's written in terms of diagonal matrices. Here it's written out in the SVD components, and maybe this emphasizes even better how the filter factors enter into the definition of the regularization error. So I call it the regularization error, but actually, my notation for that is bias, because that is how some mathematicians and statisticians would explain this, that they introduce a bias in the regularized solution. So that's important to remember. Think about the ordinary least squares solution when there's no regularization. That's actually an unbiased solution. That's an unbiased estimate of the exact solution. So it's very interesting what happens when you introduce regularization is you reduce the variance in the solution, you suppress some of the noise coming in, you add filtering. So less noise in the regularized solution, less variance. But what you pay for that is that you introduce a bias. That's how the statistician would say that. You introduce a bias in the regularized solution compared to the least squares solution. So hence the notation bias here, and I will also call it the regularization error. Okay, and then there's the perturbation error. Of course, that's the perturbation of the solution due to the errors in the right-hand side. Here's a similar expression for truncated SVD, because sometimes we also would like to actually discuss that. Sometimes it's easier to use Tikhonov regularization, sometimes it's easier to use truncated SVD to discuss things. And remember, for truncated SVD, the filter factors are like really, really easy. Either they are 1 or they are 0. Or they are 1 for the components that we retain, and they are 0 for the components that we throw away. Right? So therefore, plugging that into these expressions here, that some of these filter factors sitting here, and here are either 0 or 1, it just means that you should now look at the summations here, right? So, so it's useful to have these guys. And as I've said a couple of times, let's see. Okay, sorry, I'll go on. So if we change k, of course we change these two errors here. If we make k larger, okay, if we increase k, we include more noise components, which we can see from here because this is a sum from 1 to k. So if you increase k, we incorporate more of that. Okay, so the perturbation error grows with k. On the other hand, the bias term, the regularization error, that decreases with k, because you see this sum goes from k plus 1 to n. Okay, so if we increase k, we sum over fewer terms, and this one gets smaller. So you see, as one goes down, the other goes up. And there's got to be a k somewhere where these two guys are approximately of the same size, and then we probably cannot do much better than that. So that's what we see here. Okay. We see the norm of the regularization error. That's the blue line here. Along the x-axis here we have k, and as we increase k, sure enough, we include more and more SVD components, and the regularization error goes down as expected. And we can show that it goes down monotonically with k. At the same time, when we increase k, we see that the perturbation error increases because, as I said, we include more and more noise. So that's what's happening right there. And if we include many SVD components, we see that the noise really blows up, doesn't it? All right? And the actual error is kind of the sum of these two guys here. So we would expect the actual error to first go down and then go up, because of course the sum of the blue and the red over here cannot really feel the red one, because this is of the order 1 and this is of the order 10 to the minus 7, right? So you can't really see those guys over here. On the other hand, for large k, the total error is dominated by the perturbation bound, because the bias term is much smaller. So you have an error, a total error that like goes down, has a minimum, and then it goes up again. And sure enough, that minimum is basically where these two curves intersect each other, where they're about the same size. So again, that could be a way to choose the regularization parameter, except we can't do it, right? Because we don't know what the exact solution is, and we don't know what the error is. But that's the principle. That's what we're trying. That's what we would really, ideally, try to achieve. Somehow. Except we cannot plot these guys here. We cannot study these guys. So we have to look at stuff that is available to us instead. Something that we can compute. And definitely one thing we can compute is the residual. We can always compute the residual vector. I'm still discussing things here in terms of the truncated SVD. Right? So we can compute the truncated SVD solution. We can multiply it with A and subtract the given right-hand side, take the norm of that. That's our residual norm. That is something we can compute. So maybe we can use that for something. And again, let's do a bit of an analysis if we want to see the details. Look in the book. But basically, we can show that the residual norm behaves in two different ways, depending on whether k is small or large. All right? And of course, now there's a k eta there. That's the one associated with the Picard condition. And so let's just remind ourselves about the Picard plot. Right? And of course we have singular values going down like that. And then we have the right-hand side components. How about blue? That would decay faster in the beginning, and then they would level off here. So these would be the absolute values of ui transpose b. And here's the transition, where the noise sets in, where we can start feeling the noise in the right-hand side. So of course the good SVD components are to the left of the dashed line, and the bad guys are on the right-hand side. So these are the ones we want to retain. These are the guys we do not want. And this number here, that would actually be the number of SVD components that we should keep in our truncated SVD solution. And I call that eta k, k sub eta, because it depends on the noise level. Remember that the noise level here, eta. If you change the noise level up and down, then this point here, the transition between this guy and this guy, it shifts back and forth. So therefore, the optimal k here, of course, depends on the noise level. Okay. And when k, the number of SVD components that we include is too small, we only include the good guys. And if we write out the an approximate expression for that 2 norms squared, we do some computations, and we end up with this thing here, which is essentially a sum from k plus 1 until here k eta. So this is something that decreases as we increase k. Okay, all right? That's what I say here. Okay. If k is larger than the optimal value, that is when we're over here, when we include too much noise in the solution is dominated by noise. We can again do some computations that I skip right here, and we find this expression here for the residual, which now says that it decreases more slowly with k. So again, so maybe this different behavior of these two guys could be used as a criterion for choosing k. Definitely, it's based on the residual norm that we can actually compute. But it's difficult to devise a method that actually looks for this change, this transition in behavior here. So instead, people have come up with something that tries to catch that transition in a different way, right? And it's called the discrepancy principle. And I guess the discrepancy principle is probably the oldest, at least one of the oldest methods for choosing a regularization parameter. And the basic idea is that we should choose the truncation parameter here, the regularization parameter, in such a way that the norm of the residual resembles the norm of the noise. That's the idea. Right. So this I'm sure you've all seen that before. This is what many people call fit to the noise level, right? When the residual here is about the same size as the noise level, delta E is like a tight upper bound for the noise. Right. That would be the discrepancy principle. And so there are two issues there. We related to this. See, there's a parameter tau here, which should be slightly larger than 1. That's the idea. There are two reasons for including that. One reason is that if you want to prove things about the discrepancy principle, then you actually need this fudge factor sitting in there. It has to be slightly larger than 1. Then the theory goes through all the way. Another practical thing is that it's like a safety factor. If you happen to have a not so good estimate of your noise, in particular, if it slightly underestimates the noise, then it's good to have a safety factor in there to make sure that you don't include too many SVD components in the solution. So right, that's a discrepancy principle. It's really easy to do. Just find the lambda until this one is satisfied, provided, of course, you know, or you have an estimate of your norm. And you sometimes do that. So here's an illustration of that. So what I plot is the residual norm as a function of the truncation parameter. And sure enough, we have a residual that is monotonically decreasing, and you also see that it indeed has two different types of behavior. So when k is smaller than the optimal k, we should have a steady, fairly fast decrease of the residual norm, and once we get beyond that point, it should decrease much slower. And of course, that's what we see right here. We do see that the residual norm is coming down pretty fast here, and then it suddenly slows down right there. And then towards the end, something happens there. But you do see that behavior. And a good choice of the regularization parameter is certainly around here. And if we plug in here, the dashed line there, that is actually not just an estimate for the noise level, but actually the correct noise level. And so we need to choose the smallest k for which the discrepancy principle there is satisfied. So that means that we would choose k equal to 10. That's the first time this guy here is below that line there. So that's the discrepancy principle. And you see it indeed tries to capture this transition from the fast decay to something that is really a very slow decay here. All right? And in fact, where this happens, the actual location of this almost flat part here of the residual, that is at this level there. That's also what I write here. Up here you see square root n minus k times the standard deviation of the noise, right? So that's not a bad idea, isn't it? This discrepancy principle. If you know your noise level, it's right. It's all right. But you have to know that, otherwise what can you do? Okay? And then again, once you start surveying the literature, you'll see that of course the statisticians have also been there. They have looked at this, and they have a point here. They say that the discrepancy principle as formulated here is probably not the correct way to do things. So the thing is that if you think about truncated SVD, once you start removing SVD components from the residual, right? Then you also change the degrees of freedom in the residual. So if you're using k SVD components, you're subtracting them from your given data. So the residual has degrees of freedom that is less because you have done that. And yeah, I don't want to go into that statistical discussion there, but there's really something important here, and I think they're right. And of course, so they say that instead of the simple discrepancy principle here, you should have a modified discrepancy principle where you take into account that change of the statistical behavior of the residual once you regularize. So the right term on the correct term on the right-hand side compensates for that. But unfortunately involves something that is not so easy to compute. It computes the trace of this matrix sitting there. The trace is the sum of the eigenvalues or the sum of the diagonal elements of the matrix. And for large-scale problems, it's a bit hairy to compute those guys. But anyway, I think in principle this is actually a very good point. So why don't we all just use the discrepancy principle and call it a day? I can stop my lectures here. The only trouble is that we need this guy here. Well, that's the main trouble, because in very many applications you really have no idea what that is. And also, as we shall see later later today, it turns out that actually the regularization parameter is quite sensitive to that estimate there, and in particular, if our estimate is too small, then we compute a lousy regularized solution. So it's not so good that the method is very sensitive to that estimate there. So let's see if we can come up with other ideas for choosing the regularization parameter that are maybe less sensitive and maybe doesn't need the noise level right there. But before we do that, let's take a break here. Let's take 10-minute break here. This is a good time to take a break. Yeah.
Need the box.